We study C16, Newton's computation of pi. So we are ready to study this because we are equipped with the binomial expansion that is generalized to include the power 1 plus x to the alpha, where alpha is an arbitrary real number and absolute value of x is less than 1. That is generalized by Newton. Okay, so in 1666, it's very old, Newton applied his generalized binomial theorem to compute pi by making use of this plot. This is a semicircle of radius 1/2, r equals 1/2, and we have the origin in here. And there is a midpoint in this radius, and we have a right angle. And we would like to compute the area of this green region. We define a point on this semicircle, x comma y, and y is a function of x, as we find what this function f is. First of all, we'd like to make use of this relation. A point, a vector x, on this circle can be represented by a vector from the origin. So this is a vector x. And from the origin, I can draw another vector, that is a vector c, whose length is the radius. And from this, we find this vector is x minus c. Because the radius of this circle is r, the scalar product of x minus c to itself is r squared. The coordinate of c is this, so this is r e1/2, and this x vector is represented by x e1/2 plus y e2/2. By making use of these two relations, we can find this one is x minus r squared, and the y squared sum equals a radius squared. We know the radius is 1/2. So expand the left-hand side, and we find this r squared cancels, and y squared is x minus x squared. It is factorized as x multiplied by 1 minus x. We know x is in the region 0 to 1. So this value is positive definite except at the end point, at which it becomes a 0. Therefore, y is a positive definite except at the end point, that is completely expressed as a simple function, product of two square roots. Find the angle theta ACD. Angle ACD. ACD, this ACD, this is theta. We find this is the right angle, and this is the midpoint. B is the midpoint of AC. So this triangle is isosceles triangle. Therefore, this is the same as this. and this is r equals 1/2. So we also have 1/2 equals r. These two sides are identical to each other. Therefore, this is a theta 2, and because this is radius and this is the origin, the coordinate of D is r cosine theta and r sine theta. And in addition, the coordinate is x is 1/4, and then this is f of 1/4. But f of x equals the square root of x, or square root of 1 minus x. So this is a square root of 1/4, square root of 3/4. So this is square root of 3 over 4. So using this information, I can compute the coordinates of D as 1/4 and the square root of 3 over 4. And that is r cosine, r sine. Because r equals 1/2, cosine comma sine is 1/2 and square root of 3 over 2. This is true only for the angle for 60 degrees. Find the area S of a sector ACD. ACD. So this sector ACD, and this is the angle theta and radius r. Area of a sector is 1/2, radius squared, and angle. R equals 1/2, and theta is 1/3 of pi. So as a result, pi over 24. Find the area T of the triangle BCD. B is here. Area of this right triangle. We know this is 1/2 of radius, and this is y, and that y is square root of 3 over 4. Therefore, 1/2 base and height gives square root of 3 over 32. As a result, the area of this green region is simply obtained by subtracting s by t. Subtracting s by t. So we are left with this area. And that area is this. Next, we can express this area as an integral of f of x. We know this curve is f of x if I choose the x-axis and origin and y-axis. And this is 0, and this is here, this is the radius r, so this is 1/2 of r. That is 1/4. So this area can be expressed as a definite integral of f of x from 0 to 1/4. As a result, I can express this integral in this manner. If I make use of Newton's generalized binomial theorem, I can expand this square root in a power series of x. The reason is that I have a square root of x that is rather simple in comparison with this. So I make use of binomial theorem. Y equals minus x, alpha equals 1/2. And this one will be 1 plus alpha y, alpha minus 1 2 factorial y squared, and so on. It's an infinite series. If I simplify this expansion, I arrive at this formula. Here we have a notation double factorial. The double factorial of 3 is 3 times 1. 5 is 5, 3, 1. And 4 is a 4, 2, something like that. So product of odd numbers or even numbers is different from, similar to the usual factorial, but a little bit different. So we make use of this formula. We substitute it for the square root 1 minus x here. And then I can multiply term by term. Then, because this is x to the 1 half, so this one is replaced with x to the 1 half, 3 half, and k plus 1 half. We can make use of the integral table for arbitrary alpha. We have this expression. So we can evaluate this integral straightforwardly. Therefore, the green area of the green region, G, is simply expressed as, by making use of this integral table, we substitute this here, and here, and here, we finally obtain the series. Previously, we computed the area in an analytic way using square root 3 and pi. If I move this one to the left-hand side and multiply both sides by 24, we obtain a power series expansion, the series expansion, infinite series representation of pi. Okay, so we'd like to carry out this numerical calculation. First of all, why don't we make use of this mathematical code to compute that? First of all, I have chosen the maximum extra precision 20,000 and introduced a function f of x, f of n actually. That f of n is nothing to do with the f of x. Instead, this is a series summed over k from k equals 2 to a certain number n. That is given in here. Okay, we define this function, and why don't we make use of Mathematica to compute this by summing over everything to infinity. And then, what's next? We'd like to compute the partial sum by setting a finite value of n. The sum is until k runs to a certain value n. I'll first give you the answer for when n equals 1,650. Next, we compute this with 16,600 terms. Okay, so let's evaluate this by typing Shift plus Enter. First, it accepts the maximum extra precision to be 20,000 because I'm interested in computing the numbers by about 10,000 digits. I have enough number to guarantee the accuracy of my calculation by setting this max extra precision by 20,000. And then I asked Mathematica to evaluate the infinite sum, and it has its own table to find that it is exactly pi. Next, we compute numerical value by summing a partial sum. 4k runs from 2 to a certain number, 1,650. The result is subtracted by the actual value of pi and divided by pi to find the relative errors of numerical calculation. The result shows that the relative error is very small, and it guarantees by displayed the result in here is correct by 1,000 and a little bit more digits. Perhaps you might know very well about 3.14159265, something like that, but these are 1,000 digits. And in addition, I have carried out the calculation with n equals 16,600. The result shows that we have more than 10,000 digits accuracy. Okay, so why don't we display this number? Why don't we compute this? Some time. Okay, so this is what I obtained. You know, it is not 3.14. It does not begin with 3.14 because what I have evaluated is an exact number added. Therefore, it is not an approximation. Sure, it is an approximation because we have neglected the sum. However, it is a fractional number, a very large fractional a very large number divided by a very large number. And this remaining piece that contains the square root of 3. So you remember this term has a square root of 3. So this remaining piece is not a floating point, but a fractional number. This is a fractional number. Okay? So that does not mean it is accurate because I have terminated this series by n, and that is 16,600, something like that. So using this kind of way, we can always compute an exact number, not an exact number, approximate, but with a certain accuracy, arbitrarily, as you wish. So perhaps I believe you have never seen such kind of exact practical calculation of these kind of numbers before in mathematics class or computer class as well. So this is usual the physicists do. Find the power series expansion of inverse tangent hyperbolic. Tangent hyperbolic function is defined by this sine hyperbolic divided by cosine hyperbolic. And we have 1/2. In that case, this numerator is a sine hyperbolic and denominator is cosine hyperbolic. And this is inverse function that is defined in this region. We recall the integral table. If I make use of this, and I can express this definite integral as form log 1 plus x subtracted by log 1 minus x that can be combined into a single term as a log 1 plus x over 1 minus x. By the way, I can make use of Newton's generalized binomial theorem as long as x is magnitude of x, absolute value of x is less than 1. So in that case, this integrand can be expanded as a power series. This is nothing but the geometric series. So using this geometric series expansion, I can simplify the integrand as a polynomial. And polynomial's integral is a trivial. Okay, so it becomes like that. We know this tangent hyperbolic function is an odd function, and inverse tangent hyperbolic function is also an odd function. Therefore, this result must contain odd powers only, and even powers has disappeared. Using similar method, I can evaluate this, but actually it is another way to compute pi, even though the convergence is very poor. In principle, we can compute. Okay, so arc sine is the inverse function of sine that is defined in the region. And let us make use of the same method that we have made use to obtain the integral table or derivative table for exponential and log function. So this is by definition inverse. Arc sine is inverse of sine. We know derivative of sine is cosine, and in this region, sine is a single valued, and cosine can always expressed as a square root of 1 minus sine squared. And we can make use of the separation of variable by moving this one to the left side, by moving this one to the right side, to have a very trivial total derivative on the left hand side. And because by definition, x sine x equals sine of x, so this is dx over square root 1 minus x squared. Using this, we can construct the integral table. And by the way, why don't we apply Newton's generalized binomial theorem to expand the integrand? That the result is given like that. So using this method, I can evaluate this arc sine function as a power series of x. Okay, so using this, I can compute arc sine function as an infinite series in such a manner. So it is a very useful. Newton's binomial expansion is a very useful for our practical use. And you must remember that it is well ahead of the discovery of Taylor series expansion, and is in some cases Taylor series expansion is a very, very inefficient, and our trick to make use of the Newton's generalized binomial theorem in combination with the integration gives our derivation of a power series expansion of a certain practical functions in a very easy way. That's it for today. Thank you.